Imagine you want to predict the price of a house just by knowing its size. Sounds simple, right? But how do you exactly do that using math and data? That's where linear regression comes in. In this video, I'll walk you through a linear regression from scratch. We'll start with the intuition, then look at how math comes in, and I'll explain how linear regression works with a few simple examples. So, intuition of linear regression is very clear. It is the simplest and the most fundamental algorithm of machine learning. And the main focus of the main idea of linear regression is that we model one or more input futures and a continuous output by fitting it to a straight line. Um, to keep it in simpler terms, linear regression is just a fancy name for finding the best straight line that goes to a bunch of data points. So suppose you have a house, like data of a house, and the sizes and prices are given like 1,000 square feet house costs for 1,000 square feet cost for 200,000, 1,500 cost for 300,000, and 2,000 cost for somewhere around 400,000. So if you can see the trends here, the higher the square feet of the house, the higher is the price. But what if someone asks you out of the blue, like, what is the cost of a 1,750 square feet house? We don't know it directly, right? So, but we can draw a straight line to these data points and try to predict the price of that. This line helps us to understand the relationship between house size and price, and that's all linear regression is doing. So, the equation of linear regression is this. This y hat is called the predicted output, and this O1 is called the weight of the weight which we add, like the weight which we use for the linear combination of the inputs. And this X represents the future which we are taking in as input. And O naught represents the bias. Now, what is a bias? Bias, also called intercept in coordinate geometrical terms, is a term which we use to find the actual output, like approximate the actual output from a given equation. For example, if we take an equation y is equals to 3x, okay, so we want to find an output which is somewhere around y is equals to 10. And we don't have any bias term here. So the predicted output of y hat closest to y is equals to 10 is 9 comma 12. So 9 is not equal to 10, and 12 is not also not equal to. Here we use a simple term called bias or intercept, which is a constant which we add to the combination to make sure the values we get in the y hat are as close as to the actual values we want to predict. So here we can put the bias as 1. So 3x plus 1 will be our equation with bias or intercept. So if we now put the value of x is equals to 3, which will be equal to 10, and which is equal to y is equals to 10. So this is how bias works, and this is how important bias is. But how do we fit this best line? Like, how do we find the line which is the best line? We want the line where the predictions are as close as possible to the data points. And how do we do this? We do this by finding a loss function. In linear regression, we use the mean square error loss function, which is the difference of the actual value of y to the predicted value of y. And we square that, and we again take the average of that. For example, if suppose for a house of 1,500 square feet, the actual price is 310. 100, 3,000, but a model predicted somewhere around 300,000. So the squared error here is 310,000 minus 300,000, which is equals 10,000. Now we add all the squared errors of all data points and take the average of it. This gives us the MSC. The lower the MSC and the better the model performs. Now let's look at implementation of linear regression. So one of the most fundamental methods of implementation of linear regression is the ordinary least squares method. This is a direct mathematical formula which gives an output vector of desired weights just from one simple calculation, which is this. X represents the input future vector, Y represents the input output vector. So when we do this calculation, we get O hat, which is the output vector of all the weights which are needed for the linear combination of like for performing or for finding the best fit model or the best fit line for this data points. So now let's look at an example to understand this better. First, suppose we are given two data points. Now we want to fit these data points to a line. Y hat is equals to theta naught plus theta 1 x. So how do we perform this using OLS method? So we already know the equation of OLS method, which is equal to theta xt x to the inverse into x transpose y. So here xt represents x transpose and this represents the inverse of this multiplicative matrix and again xt represents x transpose and y represents the output future vector, which is what we desire. So we are given inputs x is equals to 1, 2, and y is equals to 2, 4. Let's add a bias column to x now because we already learned the importance of bias column. So we'll add a bias column of 1, 2x. Now we'll take the transpose of this matrix, which is equal to 1, 1, 1, 2. Now we find the value of xt x, which is equal to 1, 1, 1, 2 into 1, 1, 1, 2, which is equal to 2, 3, 3, 5. Now let's compute xt into y. Since we already know y is equals to 4, this should be equal to 1, 1, 1, 2 into 2, 4, which will be 6. Okay. Now let's find the inverse of xt. So inverse of a 2 into 2 matrix, for suppose A, B, C, D is equal to 1 by AD minus BC into D minus B minus C A. So since we already got xt x as 2, 3, 3, 5. Now, if we put the values of A, B, C, D into this equation, we'll get the inverse matrix as 5 minus 3 minus 3, 2. Now, if we compute theta hat, which is equal to 5 minus 3 minus 3, 2 into 6 and 10, we'll get 0, 2. This is the output of the this is the output of the linear combination weights vector. So now from this we can infer that theta naught is equals to 0 and theta 1 is equals to 2. So y hat, which is equal to theta naught plus theta 1 of x, is equals to 0 plus 2x, which is equal to 2x. So for the values x is equals to 1 comma 2, y is equals to 2 comma 4. These two are perfectly satisfied by this equation. So we can say that we found the best fit line for these data points. This is how Euler's method works. But the catch with Euler's method is that it only works for small data points or small sizes of data. But what if we have millions of data points? Then calculating x transpose into x and the whole inverse of that becomes very slow and even sometimes impossible. So here, instead of using Euler's method, we use a method called gradient descent. This is an iterative method, and this mainly works on minimizing the loss function. So the gradient starts with a random line and keeps adjusting the random line to reduce the error step by step. For example, if you have 1,000 steps, the main goal of this gradient descent algorithm is to reduce the error significantly by the end of 1,000 steps. So this is the formula for gradient descent algorithm. For example, as we discussed, initially we start with random weights in a descent algorithm. So the how we change this weight with each step is what this formula defines. For example, this is the initial weight, and now we change this weight um, by reducing it uh, by a learning rate into the gradient of the loss function. So this term represents the gradient of the loss function, and this term represents the learning rate. Let's say our current slope is equals to 1. Your slope is also, we call the weights of the linear combination as slope also. So let's say it is 1, and our gradient is 4, and our learning rate is 0.1 per step. So to find the new weight which fits the line better, we use the formula theta minus learning rate into, which is equal to 1 minus 0.1 into 4, which is equal to 0.6. So according to gradient descent, we can say that this weight creates a line which fits better than the previous line. So These equations or these steps are repeated for the number of epochs or the number of steps the algorithm runs for, so that at the end of n steps, the MSC between y hat and y should be minimum. So here we don't make any complex calculations for matrix inverses or matrix transpose or something. We just iterate to multiple steps, and we just reduce the weights and fit the weights, or sometimes we increase the weights if the gradient is negative, fit the weights better to the equation and find the best fit line for that. So now, if you look at the differences between OLS and gradient descent, OLS models are better for small data sets, whereas gradient descent models are like they work for data sets of with millions of data points. So in OLS models, complex computations like matrix inversions are needed, but in gradient descent, matrix inversion is not needed. You just calculate the gradient, and we just do an addition or subtraction to the weight to find the best fit line. But in OLS, we don't require scaling. But in gradient descent, we do require scaling. Scaling or normalization means that, for suppose if we have features like this, and first feature denotes uh, the price of a apartment. Second feature denotes number of balconies. Third feature denotes square feet. And this denotes Y, which is equal to the number of bedrooms. So if you look at these features, the first feature can be a very large term, like hundreds of thousands or something like that. The second feature is a negligible term, like a one or two or three, something very less compared to this. And the third feature is a medium term, like it can be 3,000, 4,000, something. But again, we need a negligible number. So here, if you can see, there's a discrepancy with the size of inputs which we are getting from the feature list. So to normalize this discrepancy, we use scaling or normalization, so that when the model performs, it it's the best decisions, and it works it performs in the best optimized way. Now let's look at a code for linear regression using gradient descent. So here we wrote a normalization function which gives the normalized of a feature list as an output. So this is the prediction function, which gives the output based on the feature list by calculating the linear combination of the weights and feature list and the bias. For example, this can be represented as x into w, summation of all these around the features or data points or columns plus the bias, and this will be equal to the y or the output which we desire. So now if you look at this function called compute gradients, this function, what this necessarily does is this gives the delta y naught value or the gradient of the wave, like loss function, which we discussed about. So dw is the gradient with respect to the weights, and db is the gradient with respect to the bias. Now, in this main function called the gradient descent, which takes in the x futures, y predictions, by values, output values we need, and the learning rate and steps. What this does necessarily does is it trains um, first by taking some random weights and then refactoring them using these gradients, which we get from the gradient function, and returns the optimized weights and bias term, which we need for the linear combination of the best fit line. So here we take n, which is equal to the number of columns or the number of, for example, futures which we look at to derive y. And initially, the random weights which we are going to take is zeros for all the futures. And bias is also we will take as zeros. And then we'll predict this. We'll predict a y hat value. And then we'll compute the gradient we'll compute the gradients for dw and dt using this y hat and y and x. Then we will reduce this as we discuss the function for reduce finding a better w is just um, reducing or decreasing the value of w into by the learn like decreasing the we decrease the value of w to the times of gradient into the learning rate, and we decrease the value of b uh, by learning rate into gradient of p. And here we are printing the loss which we get across every 100 steps as this function proceeds. I already extracted a data set called linear regression data set. So let's try this code out to check how it works. As you can see, since we're using a high learning rate, the function is taking huge steps towards minimization and getting stuck at a point here. This is called a plateau. Now let's try with another learning rate or a lower learning rate. Or if you can see, as we decrease the learning rate, um, the loss for each step is increased by because now the function is taking smaller step towards minimization. So the loss which we get at n steps is more compared to when the learning rate is 0.1. So this is how linear regression works with gradient descent. Today we looked at the intuition behind linear regression, the math behind it, different types of linear regression like the oldest model and the gradient descent one. We looked at examples of the oldest, examples of gradient descent, and we also went through the code for gradient descent and how gradient like the loss at each step changes with learning rate also is what we have seen right now. Thank you.